Hello friends, welcome to our channel. In this session, I would like to explain another important concept, that is analysis of singly reinforced section. Singly reinforced sections. See here, what is singly reinforced section? If the reinforcing bars are provided only on the tension side in the beam sections, it is called as singly reinforced beams. Means if the reinforcing bars are provided only on the tension side in the beam sections. So I will show you. So for simply supported beams, in case of simply supported beam, I will show you based on this one. So assume that this is the beam. So this is the simply supported beam. Here the reinforcement is provided at the tension side, means which is at the bottom side. Means so for simply supported beams, tensile stresses are induced in bottom layers because of positive bending moment, that is sagging. So I will writing here, this is the simply supported beam. So in simply supported beam, tensile stresses are induced in bottom layers because of positive bending moment, that is sagging bending moment. And hence the steel bars, so this is the steel bar, this is the steel bar, which is provided near the bottom of the beam. So here the cross section of the beam will be like this. This is the cross section of the beam. So if you cut this section and the steel bars, here it will be like this. So these are the steel bars. So this is the cross section of the beam. Means the bars are provided on the tension side of the beam. So what I am telling means, if the reinforcing bars are provided only on the tension side in the beam section, that is called singly reinforced beam. So I am taking the example of the simply supported beam. So here in the simply supported beam, the tensile stresses are induced in the bottom layers. Therefore, we are producing steel bars near the bottom of the beam. Okay. Then if you talk about the cantilever beam, so what is, so I am taking the example of the cantilever beam. So this is the cantilever beam. So assume this is the cantilever beam. So I'm drawing roughly. So assume this is the cantilever beam. Here, so this is the neutral axis. For the simply supported beam also exactly center there will be neutral axis. So this is the neutral axis which is indicating with a NA. So this is cantilever beam. Lever beam. So for the cantilever beam, we are where we are producing the steel reinforcement. See here, the steel reinforcement we are providing here. So again we have to give some bonding length also for the cantilever beams. So here we are providing so these are the steel bars. So in cantilever beams, the steel bars are placed near the top of the beam to resist the tensile stresses developed in top layers due to here due to the negative bending moment, which is hogging, that is hogging bending moment. So what is the difference? So in the simply supported beam and in the cantilever beam we are providing a reinforcement only on the tension side of the beam, that is singly reinforced sections, but for the simply supported beam we are providing on the bottom layers to resist the positive bending moment, but in the cantilever beam we are providing steel bars on the top side of the beam to resist the negative, that is hogging bending moment. And what about the cross section of the beam? If you see, the cross section of the beam will be like this. So exactly at the same time this is the neutral axis which is continue here like this only. So that is the neutral axis, and the if I am talking about the cross section means, so that along with the light, so the diameter of the bars will be like, so you can draw in the solid format means that is better. Okay, so I'm just roughly indicating all the things. So this is the cross section of the beam, means the reinforcement bars will provided on the tension side for the cantilever beam, and simply supported beam bottom layers, that is also tension side only. Okay, so this is the difference. So this is the example of telling what is singly reinforced sections means, if the reinforcement is provided only on the tension side of the beam sections, that is singly reinforced beam. Then coming to the point, so based on the cross section also, so according to the Euler's assumption means Euler Bernoulli. So according to Euler Bernoulli assumptions, means there is no deformation in the shape of the cross section. Means here I already told you, so for example this is the neutral axis. So this is the neutral axis. It will be continued like this only. So I am drawing the strain diagram. Based on this, there will be some assumptions. So this is the neutral axis. Okay. Here I am drawing the strain diagram as it is continuation of this member. So up to here only, up to the tension reinforcement only, this level is up to there only. Okay. So the strain diagram will be like this. So exactly up to the reinforcement only here. So this is the strain diagram. Strain diagram. Okay. So what is the Bernoulli assumption? So there is no deformation in the cross section. Means it is linear. As per Bernoulli, this will be linear. There is no deformation in the shape of the cross section. With zero strain at the so strain is denoted with this symbol. Okay, with zero strain at the neutral axis, means this is the neutral axis, and maximum at the extreme fibers, means this here it will be maximum, and here also. Why? Because what about the Bernoulli assumption? As per the Bernoulli, so there is linear in the shape of the cross section with zero strain at the neutral axis and maximum at the extreme fibers, that is at the top and bottom. So this Bernoulli assumption is valid for two different materials, means composite members also valid up to the failure. Okay, you please remember this Bernoulli assumption also. Then we'll talk about the similar concepts which is related to the singly reinforced section and the continuation of the stress block parameters. So here one more point I want to add here. This limit state method is strain oriented approach. So this is the strain oriented approach. So yesterday I told you the concept of, in the last lecture I told you the concept of working stress method. So that working stress method is a stress oriented approach. Okay, so these two are the important points which you have to add these two also. Okay, then I will show you the stress strain curve graph. Okay, stress strain curve. So in original this stress will be denoted with symbol and strain will be this symbol. So this stress strain curve, so I will draw here. So the curve will be like this. So from the center, so approximately I am drawing. Why? Because here it is not getting exactly. So I am approximately drawing. So this is also parabolic shape only, but here it will indicating somewhat linear. So that is the reason I am telling that I am drawing approximately like that. Okay, so this is the origin point, and so this is the stress strain curve I am indicating like this. Okay, and in this original stress strain curve, so here this is A and this is B. So here up to OA, this is non-linear elastic zone. This OA is non-linear elastic zone, and this AB is the crack widening zone. So up to here, this is the crack widening zone. Crack widening zone. So here stress at first crack and at B it will fails. Means you have to remember at what point you will get stress at first, at what strain you will get first crack. Means so that is the value. So this will be at 0.2%. This will be at 0.2%. Means 0.002. Similarly, B at B. So I'm drawing the exact line here also. So this is at 0.35%, which is 0.0035. Means in the original stress strain curve, here OA is the non-linear elastic zone and AB is crack widening zone. Means stress at first crack at the strain of 0.2%, and at B it will fails at 0.0035%. Means which is maximum strain. So here the first crack will be developed at 0.2% and it will fails at 0.0035. So I will explain these things while while explaining the stress block parameters also. And again in the revised stress strain diagram. So this is the original stress strain curve, and coming to the revised revised stress strain curve. Okay. So I will show you the revised stress strain curve here. So in the revised stress strain curve, what happens means this crack widening zone, means this AB zone, this crack widening zone, this AB zone made flat, and treated as plastic zone, plastic zone. So what about here the meaning? So this position will be made flat. Means like this. Like this. So it will be made flat. Okay. So this is B. So in the revised stress strain curve, this AB is made flat and treated as the plastic zone. Okay. So here also it is up to the 0. Here the strain will be maximum, that is 0.0035 only. Okay. And again based on this we have to find the design compressive strength of concrete. Okay, I will tell you that one. For characteristic compressive strength, so for finding the characteristic compressive strength, so in the generally what we have to do means we have to consider minimum 30 samples will be taken. Means for characteristic compressive strength, minimum 30 samples are to be considered. But it is not possible to test 30 possibles all the time. So therefore what we have to do means for random value to compressive strength, 3 cubes 3 cubes average at 28 days with variation should not be more than plus or minus 15%. So what I am telling generally means, so for finding the design compressive strength of the concrete, so generally what we have to do means minimum 30 samples are to be considered, but it is not possible all the time. Therefore we have to consider 3 cubes. So we already know in the concrete in what we have to prepare the cubes. For example, you can take 15 by 15 by 15 centimeters molds. In that we have preparing concrete. Like that we have to in the field. So in the laboratory, so we are considering we are taking 3 cubes. So that we have to test up for 28 days with a variation not more than plus or minus 15%. Means we have to take the average of that 3 cubes. So generally this is the FCK. So the strength of the concrete in a structural member will be 33% less than the cube strength. For example, here if you test this cube means you will get that cube strength. So for example, if you assume this cube strength will be some 100% like that. So whatever it may be. So the strength of the concrete in the structural member. So this is the cube which are directly designing in the field. But I am talking about the strength of the concrete in the structural member. Any structural member. So what about the strength? That strength will be 33% less than the cube strength. This cube strength 33% less than the cube strength. So approximately I am taking this one as 100% and this one will be some 33% lesser, means that will be you can consider as some 67% will be lesser. So that is 0.67. Okay, 0.67. So for that also I am drawing here. So don't assume this is parabolic curve, don't assume linear. So this is 0.67 FCK. Okay, so what I am telling means, so the structural member in the concrete in a structural member will be less than the cube strength, which is 33% less. Therefore I am considering 0.67 FCK. Then design compressive strength of the concrete. So already I explained this formula in the last concept. Design compressive strength of concrete equal to, so characteristic strength of the concrete in a structural member, that is 0.67 FCK divided by its partial safety factor. So what I told you in the last class, partial safety of concrete in the concrete safety factor for concrete in the limit state method, that one will be equal to 1.5. So if you simplify this one, you will get a 0.446. Approximately I am taking 0.45 SCK. Okay, so therefore design strength of the concrete what we are consider here means which is 0.45 FCK. So in the same way I am showing here. So this is 0.45 FCK. Means this is your design compressive strength of the concrete. Based on that only you have to go for the stress block parameters. So once again I am repeating the same concept up to now what I told briefly. So what is singly reinforced section? So singly reinforced section means if the reinforcing bars are provided only on the tension side of the beam, then it is called the singly reinforced section. So what about doubly reinforcements? If the reinforcing bars are provided both tension and compressive side as well as the compressive side, then it is called doubly reinforced section. So coming to the stress strain curve, here this is the original stress strain curve up to OA. So this is the non-linear elastic zone and AB is the crack widening zone. So in the revised stress strain curve, what happens means this crack widening zone is made flat and treated as the plastic zone. Okay, so this OA and this AB is the plastic zone. Then again, for that what we have to do means we have to consider for characteristic compressive strength of the concrete, we have to consider minimum 30 samples, but it is not possible all the time. Therefore we are considering 3 cubes at an average of 28 days with a variation of plus or minus 15% for obtaining the cube strength. Then so what about the cube strength of any structural member? That will be 33% lesser than that of the cube strength. And again, based on the design compressive strength formula, we are finding the design compressive strength, that is characteristic strength of the member by the its partial safety factor. You will get 0.45 FCK. So we have to design for this design compressive strength, that is 0.45 FCK. So based on that I will continue the topic. So this is for concrete. This is for concrete. So I am adding one more point here. So design strength of steel. So design strength of steel will be equal to, so that is Fy by gamma m. This Fy will be equal to 250. So already I told you the yield will be taken from 250, all the things. So the design strength of the steel will be equal to, so what about the partial safety factor for steel? That will be equal to 1.15. So totally we will get 0.87 Fi. But here I am considering 0.87 Fi. So I am taking mild steel which is 250. For example, you will get any HYHD or yield with some different metal 415 or 500. So in the formula you can substitute that value directly, you will get that one. Okay. So this also will be obtained by using the graph for the steel. So please remember this one directly. It will be very helpful to solve the problem. Otherwise the concept will be very more if you go through the graphs. Again, one more point I want to add here is, so the stress strain curve in limit state methods are considered. So the strain in steel, so the maximum strain in tension reinforcement, so which is denoted with EST, should not be less than, means like this, 0.002 plus Fy by 1.15 ES. Means the maximum strain in tension reinforcement in the section at failure should not be less than, so it should not be less than this condition, that is 0.002, because here the stress first crack will be developed. And what about this Fi? You can take any steel value which they are given. And what about this gamma m? Partial safety factor for the steel by ES. So while taking along with the formulas, you can add these things directly, you will get that one. Okay. Then move to the stress block parameters, which is very important. Okay, I will explain stress block parameters here. So based on this only you will get various formulas. Okay, stress block parameters. Okay, so I am drawing the, considering the same simply supported section, cross section of the simply supported beam. So this is the neutral axis. So here there will be steel reinforcement bars. Okay, there will be steel reinforcement bars which are at the same level only. Okay, so based on this, at this level itself, I am drawing the strain diagram. So this is at the same level height only. Okay, okay, here neutral axis will be exactly at the 0 position. Like this. Okay, so I am drawing the stress diagram. So for the continuation of this one, I am drawing the stress diagram. Here, so the maximum strain I told you is 0.0035, and stress at first crack, strain at first crack will be developed at 0.002. Means up to this level, already you people know that this will be linear, and the remaining part will be parabolic. So already I explained these things in the while drawing the graph. So I am just approximately drawing. So already I drawn all the things here in the graph. So up to the AB it will be linear, and this OA part will be parabolic curve. So here in the stress diagram I am indicating that only. Means, and up to what stress you designed, already I told you that will be 0.45 FCK. So what I explained in the last step. So the design compressive strength of concrete will be 0.45 FCK. Okay, and here this is the width of the beam from here to here, and D is the overall gross depth taken from the top to the bottom. And here one more point. So this is the cross section, and this is the strain diagram, and this is the stress diagram. So here I am drawing exactly from this line. So the here it will be strain. Okay, and one more point I want to add here, D, which is called effective depth. So effective depth means effective depth will be always taken by this overall depth minus its clear cover and minus dia bar by 2, or else you can simply remember it will be taken from the center of the dia bar from tension reinforcement to the top fiber, to the top fiber means directly we are considering from this center of the dia bar. So I am considering directly from the center of the this dia bar like this. Here this is the D, from the up to the top, up to the top. So that is the D here. D is taken from the center of the dia bar to the top, and D is the overall depth of the cross section, and B is the width of the this cross section. Under the same strain, the first crack will develop at this 0.002 level, and up to here it will be linear and the remaining part will be parabolic. So the design compressive strength of the concrete will be 0.45 FCK. So these are the important points what we have to remember in the stress block parameters. Then move to the next step. Here we are considering, so the upper top portion will be the compressive. So in the stress block parameter, what we have to remember means, so the entire this top will be so above this neutral axis. So this is the neutral axis. I am indicating here itself. Above the neutral axis, the entire cross section is compression. Okay, and below the neutral axis, the entire cross section is tension. I am indicating with a T and C like this. Okay, then move to the next point. So here I am continuing this one. So here from here to here exactly neutral axis, I am indicating this one with XU. So what is XU? So XU is the denoted with the distance of the neutral axis from the distance from the neutral axis to the top fiber. So XU is the distance, the depth of the neutral axis can be obtained by taking this one. So I am indicating with XU, from that is the distance from the neutral axis to the top fiber. And this part from here to here, it will be x2, and here to here it will be x1. So bottom one will be x1, upper one will be x2. Okay, so based on that one you have to find the exact distance, what is this one like that. Okay, so here I am assuming theta, and I am taking similar triangle of this top one, that is tan theta will be equal to, by taking two similar triangles, 0.0035 by this total distance XU for the one similar triangle, and the other triangle will be this one x1 to 0.002. So 0.002 by x1. So if I am finding x1 like this 0. So if I am taking x1 outside and simplify this one directly, you will get how much value will get means, that is 0.57 XU in terms of XU, whatever the value you will get here in terms of XU. Again x1 plus x2 equal to xu, you will take that, like that means you will get x2 value will be equal to 0.43 xu. So that is 4 by 7 xu. So the x1 will be 4 by 7 xu, and at the same time this one will be 3 by 7 times of xu. Okay, so these are the values of x1 and x2. Then the next step, we are going to find the area of the stress block. Okay, area of this stress block, area of this stress block means in the stress diagram I am going to find this area, means entire this area. So entire this area I am going to find. So if you want to find the area of this stress block, so divide this part will be rectangular and this one will be parabolic, means area of rectangle portion plus parabolic portion, means which is the area of parabolic portion. So already you people know, if it will be rectangular means you can take down base into height. What is the base? Base is x2. Here it will be x2 and here it will be x1. Okay, x2 into 0.45 fck, base into height. So that is 0.45 fck into, what about that x2? X2 already we found here, that is 3 by times of xu. That is 3 by times of xu plus, what about this parabolic portion? We know the formula for the triangle, which is half base into height. But for the parabola, 2 by 3 times of its base into height, that is 0.45. Here it will be common for this one also, fck into, and this x1 height, that x1 will be equal to this 4 by 7 xu. If you simplify these two, how much the value you will get means, that is fc 0.36. Both fck and xu will be common here. Okay, both fck and xu will be common. So finally we will get area of the stress block will be equal to 0.36 fck xu. Okay, then the total area of the parabola, and next we have going to find the distance of centroid of stress block from the top fiber. So here we are going to we are finding, so here at what distance the centroid position in this stress block. Okay, at what distance it will be. Okay, so for that we have to take the distance, it will be y or y bar. Okay, y bar. So y bar is the distance of the centroid portion from the top fiber. For finding that one, so we have the formula, that is y bar will be equal to a1 y1 plus a2 y2 by a1 plus a2. Okay, so here what about this a1? A1 is the, so for our convenient purpose I am taking this top position here and I will explain here itself. So if I explain there means it will be very clumsy. So I am dividing this line also. Okay, then so already I told you, so the entire top position will be 3 by 7 xu, and the entire bottom position will be 4 by 7 xu. Okay, this is x2 and this is x1, but so already we know the values which is similar, 4 by 0.45 fck, all the things, but here we are going to find the centroid distance. So that is indicating with from the top fiber it will be y bar, which is y bar. Okay, so what is a1 here? So a1, so we are coming from the top, this is the section, first section, and this is the second section. So area of this one, so already we know the area of that particular rectangular portion will be 0.45 fck. Okay, y bar will be equal to, so area a1 will be equal to 0.45 fck into 3 by 7 xu. And what about this y bar? So this y bar will be exactly half of the distance from the top. Why? Because we are finding the centroid distance from the top only. So y1 by 2. y1 by 2 means that is exactly 3 by 7 by 2. So means I am taking half of the 3 by 7 xu here. Okay, plus, so I am taking this plus here, and coming to this point which is a2. What about this a2? So already I told you, for the parabolic portion this a2 will be 2 by 3 times of this 0.45 fck into this 4 by 7 xu. It is better to write here. Then again, what about this y2? I am talking about the y2. I am drawing entire diagram for this y2 purpose only. Why? Because it is very inconvenient to explain in the previous diagram. So this y2 means we have to find the exact center of this one. Okay, that is the y2 means, what about this y2? Taken from the top to this center, taken from the top to the exactly center of the parabolic portion, but we know easily at what distance the rectangle centroid, that is exactly half of the distance. But for parabola it will be difficult to find the exact center position. So for that one we have to derive that things in terms of integration taken from y2 section. Again there will be lengthy problem to solve for finding the centroid. So if you taken that one means directly from here it will get 3 by 8 times of that x1, and again at some particular stage, and so up to the bottom it will be 5 by 8 times of x1, which is standard value. Remember that one, 3 by 8 x1 and 5 by 8 x1 means the centroid, the center for the parabolic portion will be 3 by 8. From here we have to find the taken from the top. So this overall distance will be 3 by 7 xu from here to here, and again up to the center position, that is 3 by 8 x1. So this y2 value will be equal to total that value, that is 3 by 7 xu plus 3 by 8 x1. So again, what about this x1? This x1 will be equal to 4 by 7 into xu, means this 3 by 8 into 4 by 7 xu. like that we have to take. So in the total x1 distance, the center will be exactly at a distance of 3 by 8. Again, what about this x1? That will be 4 by 7. Like that you have to simplify that one, otherwise it will be confused here. Okay, so then totally I am writing this value here. That one will be equal to 3 by 7 xu plus 3 by 8 into again 4 by 7 times of xu, then divided by. So what about this area 1 plus area 2? So that one will be the area of the total portion. Already we simplified that one, 0.36 fck into xu. So there will be common terms for fck xu in the upper side and bottom side. It will be cancel finally. So if you simplify that one by one, then you will get 0.42 0.42 42 xu. So if you observe here, fck will be common here and here, not xu. Xu will be xu into xu. It will get multiple times here also, like this, xu into xu. If you take xu common here in the place term and again multiply means you will take square times. Therefore, so one xu will remains like this only. So fck will be cancelled. So totally pi bar will be equal to 0.42 xu, means the distance of the centroid of stress block from the top fiber will be equal to 0.42 xu. So you please remember this value. So based on this only you will get the moment formulas, all the things. I will explain that also in the next part. So see here, already people know from the top it will be 0.42 xu. And what about from here? And what about from here? It will be at a distance of total distance will be taken from D, and remaining part will be D minus 0.42 xu. So what I am telling means I will show here. So already we people know up to here it will be 0.42 xu. So from the bottom means from here to top it will be D, and the remaining part from here to here, and the remaining part from here to here. So how much it will be? How much it will be? So it will be taken D minus 0.42 xu, which is denoted with Z. So that is called lever arm. You please remember this point, very important. So the lever arm, the distance between the line of action of compression and tension force is called lever arm, means which is taken from the centroid to the tension. So that is the distance which is lever arm, D minus 0.42 xu. Okay, this is very important while resolving the moment. Okay, then go for the forces in the compression. So I will explain here itself. So all the up to here all the things will be completed. Okay, based on that I will explain some more formulas. So forces, compressive forces. So compressive, so forces in compression. Forces in compression. So that one will be equal to. So what is the force here? Already we people know. Stress equal to force per unit area. So if I want force means I will take stress into its area. Okay, just vice versa. Just cross multiplying. Stress into its area. Okay, so what about the stress here? So average stress. So average stress means already we obtain the force up to here will be 0.36 fck. So if you observe this stress diagram very clearly, so what is the compressive force? So average stress we are finding at So already I told you the formula, based on the formula. So area of the stress block. So area of the stress block will be 0.36 FCK into XU. Overall area I told you that one. So here stress is 0 at this neutral axis position, and already the design strength we are taking 0.45. So if we find the based on the area, you will get 0.36 FCK, which is the average stress here. So that is I am taking here 0.36 FCK. And what about its area? So we people know that B into XU in the compression side. So which is totally force in compression will be equal to 0.36 FCK BXU. So already we found that area of the stress block, that is area of the rectangular portion plus area of the parabolic portion. There you find out that 0.36 FCK stress, which is average stress in the entire area. Okay. Then force in tension. Forces in tension. That one will be equal to design yield stress. Yield stress into area. So design yield stress will be, already I told you, the based on the formula, that one will be 0.87 Fy into its area, means which is in the bottom side, that is area of the steel. I am taking as it is like that only, as it is like that. Okay. So that is 0.87 Fy. So these are the forces in the compression and tension. So that is 0.36 FCKB into XU, and here at the tension side it will be T equal to, and this is for C for compression, which is equal to C, and the T will be equal to this value 0.87 Fy, area of the steel. Okay. Then based on that we have to find that for example, if you take this, compression will be equal to tension, means what is the value, 0.36 FCK B into XU equal to 0.87 Fy, area of this steel. So if you want the depth of the neutral axis, okay, depth of the neutral axis, so I am taking XU outside, means then if you simplify this one, area of the steel divided by 0.36 FCK into B. So directly we will get a depth of the neutral axis value. So that is the way to find the depth of the neutral axis. And so finally, based on this, we have to find the moment also. So that is the last point in our session, which is moment. So already we people know that moment. What is the moment? Moment is the formula for force into its perpendicular distance. So for example, if you want the moment, so for example, if you observe here, so I want the force in the compression. So compressive moment. So moment due to compressive forces. Okay, that one will be equal to force into its distance. Okay, that is 0.36 FCK into B into XU. And again, what about this distance, which is lever arm? That is D minus 0.42 XU. Then we have to find the moment due to tension, means whatever the forces, this force into its perpendicular distance. So I am showing here this force into its distance, means the force will be 0.87 Fy, area of the steel, into D minus 0.42 XU. Again this XU based on the balance section, all the things up to you here. You please remember all the things. So in the next session I will continue the remaining topic. Thank you so much.